Hey folks, this is our last lesson in our magnetism unit. We're going to be talking about electromagnetic induction and then using that information to talk a little bit about motors and generators, which are specific applications of some of what we have learned these past few days about magnetism and electricity. So I've got two main goals for this lesson. First is to be able to explain how we can use a magnet to induce a current in a section of wire. And then secondly, we're going to talk about motors and generators and how they work, and more specifically how they're different from each other. What you'll find is that these two very common devices are basically the same thing, just sort of operating in reverse of each other. Now, in class, I asked you to try to figure out the answer to the first goal on your own, how to induce a current just using a magnet. So I gave you this setup right here, where we've got a coil of wire just looped around and around. And then that's hooked up to our multimeter, which has been set to measure current, aka it's functioning as an ammeter right now, trying to determine the amperage of the current running through that coil. And then we've also got a bar magnet over here. Okay, and so the goal is to figure out how to use this bar magnet to induce a current in this wire so that we see a reading show up there. Now, you may notice that, oop, things are happening already. Okay, but then in the end, it always kind of comes back down to zero as soon as I stop doing what I'm doing. Now, a number of people will often try placing it here, and again, we get a little bit of a reading, but then it always ends up dropping down to zero. A number of people will try putting in the middle, and they start seeing something, but then again, it drops down to zero. So you try different locations here, and you're trying to fine-tune it. But in the end, what you'll always end up finding is that it always drops back down to zero as soon as you make it stop moving. But if you keep moving the magnet back and forth, creating this changing magnetic field, then we get a very substantial reading of our current. Okay, so hopefully what you can deduce from this information then is that in order to induce a current in a section of wire, we have to move a magnet around it. In other words, create a changing magnetic field. Okay, the same way that a charge has to move in order to create a magnetic field, a magnet has to move in order to induce a current. It's the same sort of idea here, where we have to have motion in order to go from magnets to electricity or vice versa. What you might also notice is that the faster that magnet moves, or the bigger the magnet is, etc., the bigger the current that will be induced as a result of it. Okay, so that's the big idea here, is that anytime we are moving a magnet around a wire, we can induce a current in it. That's the big idea. Now, to go a little bit further, what some people will notice is that it's kind of interesting. When I take the North Pole, for example, and I push it in, I end up with a negative current, and then when I pull it out, I get a positive current. So again, negative as it goes in, then positive as it comes out. And then if I switch it around so that now it's the South Pole, then what I see is the opposite happening. When it goes in, it's positive, and when I pull it out, it's a negative current. Again, in it's positive, and out it's negative. Okay. Now again, the positive and negative just refers to the direction that the current is traveling, whether it's going from this wire over to this wire or vice versa. So what this tells us then is that which pole of the magnet is going in, as well as the direction that it's moving in, will change the direction of the current that's induced. Now this next slide that I'm going to talk about is advanced. We're talking level 5 stuff here, so if this kind of has you freaked out, by all means skip to the next slide. Don't let it worry you. But just in case you are interested, okay, the way that we can determine which way the current will travel as a result of this changing magnetic field can be determined using something called Lenz's law. Okay, now Lenz's law basically states that that coils are kind of ornery and don't like change, is the basic idea. So by creating this changing magnetic field, what we're doing is we're creating either a stronger or a weaker magnetic field running through our coil. And you can kind of think of it as The coil doesn't really like that. It doesn't really like to have a big change in the magnetic field. It would like to keep it the same. So what will happen is there will be a current induced so that our coil becomes a solenoid. And the magnetic field of that solenoid will oppose the change in the magnetic field that's being produced by the magnet. Okay, so for example, let's say, okay, I take this north pole here and I push it in to the solenoid, okay? So I'm basically increasing the strength of sort of this north magnetic pole going through the solenoid. What this is going to do is it's going to create a current running through the solenoid, so that the solenoid creates a new magnetic field with the north pole pointing the opposite way. Okay, so basically the whole purpose of the current being induced is to create an opposing magnetic field that will be going the opposite way relative to the changing field that I'm producing. So if I increase the north pole field strength going this way by pushing this in further, my solenoid is going to create a new magnetic field going the opposite way to kind of counteract or offset that change in magnetic field, if you will. Again, I know that's kind of tricky stuff, so if you are totally freaked out by that, please don't be. I'm not going to test you on it. But for those of you who think that that's interesting, like me, now you know, and now you have a specific law to look up to help you better understand this idea. Okay, so now that we know some basics about electromagnetic induction, we can talk about a couple of devices that are useful, namely motors and generators. Okay, now motors we have dealt with in the past, hooking them up to circuits. We see that they can convert electrical energy into mechanical energy, hook them up to a current, and they cause things to spin. Okay, now it turns out that generators, things that can generate electricity as a backup when we don't have access to the grid, for example, behave very similarly, just sort of in reverse. So what we have here is a diagram of both a motor on the left and a generator on the right. And in each of these situations, what we have is a loop of wire that's located within a magnetic field. We see we've got two magnets here, a north pole and a south pole. And then this loop of wire, which is able to rotate within that magnetic field, spin around and around and around, so that sometimes the two sides there are really close to the two poles, and sometimes so that they're dead center between the two poles. So it just rotates around and around and around. Same idea for the generator. The difference between these two is the kind of energy that's put in and the kind of energy that comes out. Okay, so to compare the two, with a motor, as I mentioned, we're converting electrical energy into mechanical energy. So the basic idea with this is with a motor, we have this loop of wire and we attach it to a battery so that we get a current running through it. Okay, so we can imagine the little current going on, running through this wire. Okay, at this point, the magnetic field is going this way between the two magnets. Okay, the charge is moving along this way, and if we notice that charge is moving perpendicular to that magnetic field, what that tells us then is that we can use the right-hand rule to figure out the force being exerted on that charge, which, as it turns out, will always be kind of pushing it around and around in a circle. Okay, now I know that can be kind of hard to visualize, so when we're in class we can definitely pull some stuff out and play with it a little bit more. But the idea is, through the magic of the right-hand rule, we are able to keep this loop constantly turning round and around and around in a circle due to the magnetic force exerted on this moving charge in this magnetic field. That's how we're able to convert this electrical energy into mechanical energy and cause there to be this constant motion as a result of it. Okay, whoops, wrong way. Now with a generator, similar idea, similar setup, but it's the opposite in terms of input and output. The idea with a generator is that we are inputting mechanical energy and getting electrical energy out of it. Okay, so the way that this works, whoops, wrong way, there we go, okay. The way that this works is, instead of this time hooking up our loop of wire to a power source, instead what we do is we mechanically crank it around, okay? So like just using, a crank for lack of a better term. We physically cause the loop of wire to spin around in that magnetic field. Now what that does, what it feels like to the loop then, is it feels like the magnets are moving. Okay, it doesn't really matter whether the loop is moving or the magnets are moving. The idea is for the loop there is a changing magnetic field as a result of this, since it's spinning around, and you know, 1 minute this side is closer to the North Pole and the next minute this side is closer to the South Pole, and oh my gosh, it's going around and around and around. Okay. We know that when there's a changing magnetic field experienced by a loop of wire, that loop of wire is going to try to counteract that change by inducing a current as a result of it. So what we would find then is that by changing that magnetic field, by moving this loop, rotating it around within this magnetic field, we're going to induce an alternating current as a result of it, as this loop is constantly creating new magnetic fields to try to offset the change that it's experiencing. Okay. Pretty weird. So those are just the very basics of motors and generators. I think that's all I have to tell you guys. I'll see you in class. Take care. Be good.